Hello there, and welcome to Whispers of Earth, the place where we let curiosity wander without a timer and give big questions the time they deserve. This isn't the sort of space for rushing through bullet points or hurrying to the end. Tonight, let's step softly into a time so distant it feels like a dream. Hundreds of millions of years before any forest, before any bird, before the first fish found a fin. The continents wore stranger names. The sun was a little dimmer, and the oceans carried a chill that would one day deepen into silence. This is the story of Snowball Earth. When ice crept from the poles, crossed the mid-latitudes, and, if many clues are right, reached almost to the equator. Imagine coastlines erased by glaciers, waves sealed under a skin of blue-white glass, and a sky made sharp by frost. We begin not with catastrophe, but with a subtle drift. Over long ages, volcanoes breathed out carbon dioxide, while mountains weathered down and locked that carbon into rock. The balance teetered, as continents slid beneath a sun that hit them at just the wrong angles. Ice sheets gained ground. White surfaces reflected more sunlight back to space, and the planet grew cooler still, a feedback loop of brightness and cold. The oceans stiffened at their edges. Snow fell where rain once wandered. The world's color palette narrowed to pale blues, pearl grays, and the dark ink of open water shrinking away. If you stood on one of those ancient shores at the start, you might have felt the first season that refused to end. The wind would sing across a frozen bay. The horizon would be a wall of ice, its face striped by years like rings in a tree. And beneath your feet, the rocks would keep quiet notes about what was happening. Pebbles dropped by icebergs into muddy sea floors, later to harden into stone and carry a message across time. The signature of glaciers at latitudes that should have been warm. But silence is never the whole story. Even in the coldest chapters, the planet kept breathing. Volcanoes did not stop their slow work. Deep on the sea floor, at places where Earth's plates part and new crust is born, hot water pulsed out of black chimneys. Around those vents, life gathered, huddled in the dark, feeding not on sunlight, but on chemistry. In tide-cracked leads within the ice, thin oases of open water may have formed, where microscopic drifters could still catch a photon and split it into energy and hope. Snowball Earth is not just a tale of freezing. It's a lullaby about endurance. The ice advanced, yes, but so did time. Carbon dioxide, unable to wash quickly back into rocks under a frozen hydrologic cycle, began to build in the air with every volcanic sigh. Slowly, invisibly, a counterspell was being cast. And when the day of thaw finally came, it would be sudden, global, and transformative, like dawn breaking after a night that lasted millions of years. For now, let your shoulders drop. Picture the planet wrapped in a quiet, reflecting coat, and feel how even in stillness, processes are moving. Geology thinking in centuries. Biology in heartbeats too small to see. This is where our story starts, at the edge of ice, listening. To understand nights so ancient, we listen to quiet storytellers, rocks that learned patience. Along old coastlines lifted into mountains and cut by rivers, geologists find pages from the snowball chapter, evidence chilled into stone. One page looks like a muddy notebook torn by pebbles. Imagine fine layers settling gently in a calm sea, paper-thin bands of clay and silt. Then, out of nowhere, a rounded cobble punches through those delicate layers and comes to rest like a meteor in soft paper. That cobble is a dropstone, carried by an iceberg, released as the ice melted and stitched forever into the sea floor. When those layers harden, the story becomes legible, ice above water that should have been warm. Another page is rougher, a messy rock called a diamictite, a natural collage of sand, silt, and stones of many sizes jumbled together. It's the fingerprint of glacial grinding and dumping, the work of ice that bulldozed landscapes and let the debris go when it met the sea. Sometimes you can run your fingers along a polished slab and feel striations, parallel scratches carved by rocks frozen into the base of a moving glacier, writing lines the length of a hillside. And then there's a subtler voice, a compass held inside a stone. Tiny iron minerals like magnetite align themselves with Earth's magnetic field as sediments settle or as lava cools. Millions of years later, that alignment can still be measured. In some snowball-aged rocks, the direction they point whispers something astonishing. These glacial deposits formed near the equator. The idea sounds like a riddle. Tropical glaciers? Until you see the data repeat across continents that were once neighbors. Piece by piece, the picture grows. Low-latitude ice, iceberg scars in ancient mud, global signals layered like a quilt. Between these pages lie pauses, intervals when seas briefly opened, winds shifted, or volcanoes pressed a little more warmth into the sky. But the overall tone remains wintry, a long-held breath. If you listen closely, the rocks also hint at how the world would thaw. Above some of those glacial layers lies a sudden change. Creamy, chalk-like bands of carbonate that seem to cap the cold stones, as if a warm ocean rushed back and painted the seabed in limestone. We'll walk into those bright layers soon. For now, it's enough to know that the planet's memory is careful, and that even after hundreds of millions of years, the script of ice and light can still be read with a gentle touch. Sometimes a change that seems gentle at first becomes a landslide. Snowball Earth begins that way. Quiet numbers drifting toward a threshold. Then a sudden slip into cold. Think of the planet's surface as a mirror that can grow brighter. Bare rock and open ocean are modest mirrors. Ice and snow are brilliant ones. When white grows, more sunlight bounces back to space, and the world cools, letting even more white spread. It's a loop with a favorite direction. But what gave the ice its early foothold? Over long spans, continents wandering through the tropics wore down under warm rain. That rain, slightly acidic with dissolved carbon dioxide, worked like a slow broom on silicate rocks. The chemistry tucked atmospheric CO2 into minerals and clay, then carried the carbon to the sea to be buried. Less CO2 meant a fainter greenhouse blanket, and global temperatures slipped. At the same time, Earth's crust was restless. Supercontinents had broken and stitched themselves more than once, laying out fresh volcanic rock that weathers quickly, especially under tropical sun and storm. Picture dark, newborn stone spread like a runway for rain, pulling carbon from the air with uncommon eagerness. With continents straddling low latitudes, that weathering engine ran hot, even as the world cooled. There's a critical line in this story: the latitude where sea ice can survive the summer. As the planet cooled, that line crept equatorward. For a while, seasonal melt kept the oceans breathing, dark water opening each year to drink sunlight. Then the line crossed a point of no return. Bright ice pushed far enough into mid-latitudes that the mirror effect took over. More reflection meant less warmth. Less warmth meant more ice. Winter stopped leaving, and the open ocean narrowed to threads and polinias before sealing almost completely. The skies changed too. Colder air held less moisture, thinning clouds and softening the greenhouse effect of water vapor. Winds sharpened, contouring snow into dunes, scouring coasts where tide met ice. Beneath that armor, the ocean still moved, slow, dense saline, carrying the memory of currents under a ceiling of glass. It's tempting to call this a failure of balance, but it's also a kind of order. Planetary systems follow rules, and when the inputs line up, low CO2, eager weathering, brightening ice, those rules usher the climate into a different state. The Earth didn't decide to freeze. It crossed a threshold written in physics and light. Close your eyes and imagine the last slush giving way to a continuous blue-white lid. Somewhere far below, volcanoes rumble softly, their breath rising molecule by molecule into the cold. That breath will matter. For now the world has tipped. The long night gathers. Picture an ocean wearing a lid, blue-white, bright enough to sting your eyes. Sea ice stretched almost from pole to pole, in places tens to hundreds of meters thick. On land, glaciers swelled into slow mountains of moving glass, a kilometer tall in places, their bases grinding valleys into bedrock. At first glance, it feels like a planet paused, but the ocean below did not sleep. Under the ice, water still flowed. When sea ice forms, it rejects salt, sending dense, briny fingers downward that help drive circulation. In the dark, those slow currents ferried nutrients, stitched together basins, and kept the deep from becoming a stagnant tomb. Along the seams where plates spread and volcanoes quietly stitched new crust, hydrothermal vents blew hot, mineral-rich water into the cold. Around those chimneys, black smokers, white smokers, crowds of microbes fed not on sunlight but on chemistry, tugging energy from hydrogen, methane, and sulfide. In their company, life folded itself small and stubborn, building ecosystems with patience instead of speed. Even the ice itself was not empty. Sea ice is a cathedral of pores and channels, tiny hallways where brine trickles and microbes can cling. Some produced protective sugars to keep from freezing. Others turned scarce nutrients into a slow trickle of growth. Where winds tore open leads or tides flexed the crust, ribbons of open water appeared, polynias like breaths in a sleeping body. Through those thin windows, sunlight spilled into the upper ocean. For a few precious hours or days, photosynthetic plankton could wake, bloom a little, then fade when the lid closed again. It wasn't much, but it was enough to keep threads of the food web from snapping. Dust still fell from the sky, volcanic ash, rock flour ground by glaciers, the fine breath of deserts. Dark grains scattered across the ice could melt shallow cryoconite hollows, tiny bowls that captured light and heat. In each one, a private world, meltwater, microbes, faint whiffs of oxygen. Multiply that by millions, and the word sterile begins to feel untrue. At the foot of continental ice, where glaciers met the sea, grounding lines hid other oases. Geothermal warmth seeped upward. Subglacial rivers carried minerals out from under the ice, making plume-like halos where they entered the ocean. Each contact zone, ice meeting rock, heat meeting cold, darkness meeting a thin ribbon of day, was a chance for life to persist. This is the quiet lesson of Snowball Earth. Survival favors the adaptable, the small, the communities that can feed on chemistry when sunlight is gone and bloom quickly when it returns. The planet wore a mirror, but beneath it, metabolism continued. And above, in an atmosphere that could no longer scrub out volcanic breath as quickly, carbon dioxide crept upward, molecule by molecule, building toward a tipping point of warmth. Close your eyes and listen for it. The faint hiss of a hydrothermal vent, the pop of brine in ice channels, the whisper of wind pressing a lad open. The world is cold, yes. It is also alive. Even when the world wore ice to the equator, the interior did not forget its fire. Along mid-ocean ridges, at island arcs, and in lonely hot spots, volcanoes kept exhaling, slow, tireless, indifferent to weather. Each plume carried carbon dioxide into a sky that had little power to wash it away. With rivers locked beneath ice and chemical weathering idled, the usual sink for CO2, the silicate rocks that drink it down, fell quiet. So molecule by patient molecule, the air thickened. You wouldn't see it with your eyes. The sky would look as clean as glass, the stars close enough to touch. But in the infrared, where warmth tries to sing itself back to space, the new blanket gathered notes and held them. Year by year, radiative whispers grew into a low, steady hum of heat. At first, ice shrugged it off. The planet's bright shell still bounced most sunlight outward. Yet even mirrors have seams. Dust helped. Winds racing over bare glacial plains lifted fine, dark flour and spread it across the ice. Volcanoes added ash, another quiet darkening. In summer light near the equator, thin but faithful, patched surfaces began to sip rather than reflect. Blue melt ponds opened like eyes. Each pond drank more heat, widened, connected with its neighbor. The albedo feedback that once tightened the freeze now loosened it. With the first real melt, water vapor joined in. Air that had been starved of moisture began to hold it, and water vapor is a greenhouse partner of uncommon strength. A new loop spun up. More melt, more vapor, more warmth, more melt. Beneath the ice, the ocean responded, currents quickening as fresh meltwater feathered the surface, and density contrasts shifted. Crevasses deepened. The lid thinned. It did not break everywhere at once. Nothing on Earth truly does, but the direction was set. Somewhere, a glacier's snout collapsed into glittering bergs. Somewhere, a polynia refused to refreeze and instead widened into a lane, then a bay, then a sea. Clouds fattened, snow turned to sleet, sleet to rain. And when the tipping came, it must have felt like a planet exhaling after an impossibly long breath. Runoff roaring, coastlines surging forward, the air heavy and warm in a way that would have seemed unreal a million years earlier. The thaw was not gentle. A greenhouse sky swollen with CO2 likely swung the world from deep freeze toward hothouse, flooding the oceans with fresh water from melting ice and with ions from rock suddenly exposed to storms. Rivers chewed new valleys in a geologic heartbeat. On continental shelves, chemistry pivoted fast, the stage setting for strange, creamy rocks that would later rest directly atop glacial debris. The cap carbonates, bright signatures of a world coming back to blue. For now, hold this image. A white planet stitched with widening rivers of melt. The air thick with the breath of volcanoes, the first rains in an age tapping on ancient ice. The spell is breaking. When the ice finally loosened its grip, the planet did not simply return to the old normal. It rushed into a new brightness. Rivers carved fresh lines through raw, unvegetated rock, carrying floods of dissolved minerals, calcium, magnesium, bicarbonate, down to the sea. The oceans, shocked awake by warmth and fresh water, turned chemically rich, almost overfull, and then something beautiful happened. The water began to lay down stone like frosting. Geologists call these layers cap carbonates. Imagine a pale, creamy blanket of limestone or dolostone draped directly on top of dark, scratchy glacial debris. No long pause, no missing pages, just cold rock, then warm carbonate, touching. In outcrops today, the contact can look improbable, as if two chapters from different books were pressed together. But they belong to the same breath. The first exhale after the long freeze. Why this sudden coat of white? During snowball time, volcanic CO2 gathered quietly in the air, while weathering, the great chemical broom was stalled beneath the ice. When the thaw came, that stored greenhouse warmth lingered, and rainfall returned in torrents. Freshly ground continents offered enormous reactive surfaces. Weathering roared back to life. River waters swelled with carbonate ions, and the seas became supersaturated, ready to crystallize minerals the moment conditions allowed. Needle-like crystals grew, fans splayed, and fine muds settled into soft, chalky beds that would harden into stone. If you could have waded there, ankle-deep on a newborn shelf, you might have felt the seafloor changing underfoot, grains turning to glue as microcrystals locked. In places, odd shapes rose, low mounds, teepee-like buckles, ripples larger than the wind alone could sculpt, all signs of a chemistry racing to catch up with climate. Each structure was a note in a song about feedbacks reversing. From bright ice that amplified cold to bright carbonates that recorded heat and rain. There's a gentleness to these rocks when you hold them, the way they break, the soft powder on your fingers. But their message is daring. Climates can pivot, and life inherits the consequences. The cap carbonates smoothed the scars of ice with a pale veneer, and beneath that veneer, ecosystems would soon reorganize. Nutrients flushed from land into sea, circulation patterns shifted, and oxygen began to pulse more reliably through shallow waters. The stage lights brightened for organisms waiting to expand. Let this part of the story settle like quiet dust. A world that went white with ice now goes white with stone. The two mirrors facing each other across a thin boundary. In that brightness, opportunity spreads. The ocean's chemistry, once a constraint, becomes a gift, fertility written in ions and rain. After the ice stepped back and the pale cap settled over seafloors, the ocean felt new in its own skin. Fresh water from melting ice poured off raw continents, rich with ions scraped from rock faces that hadn't seen rain in an age. Rivers ran milky with life's ingredients, phosphate, nitrate, silica, and the sea accepted them like a long-awaited meal. Circulation patterns shifted as the surface warmed and freshened. Where the snowball lid once kept the ocean dark and stratified, wind now wrinkled open water, storms mixed layers, and sunlight could reach deeper. With every wave and overturn, oxygen crept farther from the air into the sea, breaking the old habit of suffocation in quiet basins. Places that had been starved began to pulse with breath. Microscopic drifters answered first. Imagine an April that lasts for years. Blooms of algae rising in soft green tides over continental shelves, then fading and sinking, feeding bacteria, feeding sediments, feeding the chemistry that would keep oxygen hovering longer above the seafloor. Each bloom stitched a thin line of carbon into mud, a little savings account for future time. The ocean was learning a new rhythm: daylight, growth, reign of organics. Repeated not just seasonally, but geologically, patiently widening the space where complex metabolism could wander. In this renewed sea, iron told a parallel story. During the deep freeze, anoxic waters let dissolved iron accumulate. With thaw and oxygen's return, that iron met its old rival and fell as rust, layering certain basins with reddish bands, a quiet encore of iron formations long thought belonged only to earlier eras. Rust is a small word for a large transition. It marks boundaries between breathless and breathing waters, between constraint and possibility. Oxygen did not rise everywhere at once, and it did not rise forever without stumbles. But shelves, those bright, shallow margins where rivers meet waves, became laboratories for change. More oxygen meant more energy per mouthful, opportunities for cells to get bigger, bodies to scaffold with collagen, shells to experiment with minerals. In the soft muds above the cap carbonates, fossils would later show strange quilted forms and ripple-bodied creatures testing the idea of being many cells together, moving as one. Stand with me on that newborn shore in your mind. The light is warm, the sky a little hazy with CO2 that will, in time, be drawn down by weather and life. Waves lift and set, patient as breath. If you listen, you can almost hear the chemistry turning, a quiet click as limits loosen and options multiply. The ice did not just end, it prepared a stage. To make sense of a night this long, we give it names. Soft lanterns along a dark path. Geologists call the great freezes of the Cryogenian by two that feel almost musical, Sturtian and Marinoan. They are not just labels, they're anchors, chapters stitched to dates, rocks, and places where the story stands still long enough to be measured. The Sturtian comes first. Think 720 million years ago. Give or take the careful breaths it takes to count zircons in volcanic ash. In canyons and road cuts from Australia to Canada, China to Namibia, you can lay your hand on a rough, unsorted rock, glacial diamictite, resting where a quiet sea once spread. Within it, loner stones sit like commas in a thundery sentence, dropped from icebergs into fine mud. Above and below, layers tell of pause and persistence. The sea goes on, even when the world is cold. After a long run of winters measured in millions of years, the Sturtian relaxes. Oceans open more each summer. Chemistry leans warm. Then, after an interval of breathing, rivers learning their banks again, shelves hosting modest blooms, the planet slips a second time. The Marinoan arrives, later in the Cryogenian, around 650 to 635 million years ago. Its fingerprints look eerily familiar. Low-latitude glacial debris, striated pavements, dropstones in muds that should have known only rain. Two movements in the same symphony, similar notes, different crescendos. How do we know the timing? Tiny clocks. When ash from distant volcanoes settled into basins, it carried zircons, mineral crystals that trap a record of radioactive decay. In labs bright with microscopes and patient hands, those clocks are read grain by grain. The numbers, cautious and cross-checked, give us ranges, not rigid walls. Enough to sketch a timeline where ice advances, lingers, and steps back. And at the top of each cold chapter, Like a pale curtain drawn across the stage, lie the cap carbonates you've already met. They're part signature, part exclamation point. Creamy carbonates draped directly over glacial rubble. In places, they hold odd textures: crystal fans, teepee buckles, mammoth ripples. Each is a whisper that says, warmth returned quickly, and the sea was busy. Between Sturtian and Marinoan, the world wasn't idle. Continents wandered. Mountain belts rose and weathered. The balance of gases tipped and rebalanced. Life, small but tireless, persisted in vents, in ice brine channels, in brief open waters, ready to surge when the ceiling lifted. The rhythm feels slow to us, but to geology, it's a heartbeat. Freeze, thaw, breathe. Say the names softly, Sturtian, Marinoan, and feel how they turn the abstract into something you can hold. Two polished stones in a pocket, warmed by your palm. They remind us that even grand climates arrive in episodes, with overtures and codas, rests and reprises. Close your eyes and picture the planet as a mirror, white from pole to pole. Now, with the same care, imagine hairline cracks in that mirror. Lanes of thin ice, ribbons of open water, places where wind and tide kept the surface breathing. Between these two pictures lives a thoughtful debate. Was Earth a true snowball, sealed almost completely, or a gentler slush ball, with equatorial leads and seasonal blue? The rocks speak in more than one voice. Low-latitude glacial deposits, striated pavements, and lonely dropstones in calm water muds argue for severe global cold. Ice at tropical latitudes where palm-like ferns would someday sway. Bright cap carbonates draped right over glacial rubble hint at a rapid planet-wide thaw, the kind you'd expect if a hard freeze finally broke. These are strong notes in the snowball song, but other details hum a softer tune. Some cap carbonates preserve giant ripples and textures that look like they formed in energetic, wave-touched waters, hard to imagine under a roof of ice meters thick. Certain chemical signals and sedimentary structures suggest that, at least in some basins, surface waters stayed connected to air, or reconnected often enough to matter. Models, too, sometimes find that even in a deep freeze, winds can pry open leads, tides can flex seams, and the tropics can keep pockets of thinner ice that let just enough light through to power small photosynthetic oases. Perhaps, as is so often true, the truth wears both coats. Snowball need not mean perfectly uniform, any more than winter means the same weather in every town. Sea ice can be thick here, thin there. Dust and ash can darken patches. Melt ponds can cluster. Polynyas can persist along coasts. If there were narrow belts of open water, or seasons when sunlight gnawed the lid back for a while, that would have offered lifelines, a breath of oxygen, a pulse of primary production, corridors for nutrients to cycle and for ecosystems to hold on. What matters for our story is that the climate state was profoundly different from today. The albedo feedback had the upper hand. Chemical weathering on land was largely idled. The ocean's surface, whether sealed tight or stitched with narrow windows, was a barrier that changed how heat, gases, and life moved. In that altered world, survival favored flexibility, microbes that could feast on chemistry in the dark, or sprint through a sunny bloom when a lead opened. Communities tucked into vent fields, brine channels, and subglacial seeps. So was it snowball or slushball? The rocks give us strong boundaries and generous room inside them. Earth was very cold for very long, and then it wasn't, fast. The details inside that sentence hold the texture of life's persistence. And when the ice finally yielded, those textures became the threads that complex life would later weave into bodies, behaviors, and ecosystems we can recognize. Breathe in, breathe out. However we name it, the lesson is the same. Even under a mirror of ice, the planet kept its options open. Climate can hinge on where the land chooses to sleep. During snowball times, the supercontinent Rodinia was coming apart, rifting into pieces, opening newborn oceans, laying out long tropical coastlines like dark runways for monsoon rain. Warm rain on fresh basalt is a powerful broom. It scrubs CO2 from the air and tucks it into minerals, weakening the greenhouse and tilting the world toward cold. Picture rifts glowing with young lava, mountains raw and dark, edges of continents dropped to sea level, where waves could grind them to flour. In the tropics, sunlight and storms accelerate chemical weathering, so every afternoon thunderhead helped pull a little more carbon from the sky. The math is slow but merciless. Enough fresh rock in the right latitudes, and the planet's heat budget slides. Those drifting plates also reshaped currents and winds. As gateways opened and closed, oceans found new paths. Heat moved differently from equator to pole. Long belts of shallow seas, bright, easily iced, wrapped low latitudes. Once ice found a foothold there, reflection did the rest. A paler planet returned more sunlight to space, tightening the chill. The breakup did something else. It multiplied margins. More continental edges mean more places for nutrients to wash to sea, more shelves to host life when conditions allow. That matters after the thaw, but even during the freeze, tectonics set the chessboard. Volcanoes along rifts kept exhaling CO2 into a sky that couldn't easily clean itself under ice. The same forces that helped start the freeze were also winding the spring that would snap it back. If you could hover above that ancient earth, you'd see scars of separation, faults like handwriting across continents, narrow seas tugging plates apart. Nightly lightning would stitch along equatorial coasts. Morning mists would rise from hot, fresh rock. Down in the mantle, slow convection shouldered continents like rafts. Up at the surface, every meter of coastline was a conversation between air, water, and stone, deciding how bright the planet would be. This is the strange poetry of plate tectonics. By moving rock, it moves climate. Supercontinents gather and scatter. With each cycle, river routes, mountain heights, and weathering engines change. In the cryogenian, the geometry favored a slide into ice. Later, as CO2 gathered and warmth pushed back. That same geometry, those long shelves and hungry margins, would help the ocean breathe, fertilize blooms, and invite complexity. Hold the image of a jigsaw slowly coming apart, pieces drifting under a pale sun. The pattern isn't chaos. It's a rhythm deep in the planet, one that life had to learn to dance with. Snowball Earth is one verse in that longer song. Hidden in landscapes and rainstorms is a quiet device that steadies climate over deep time, a thermostat made not of metal and wires, but of mountains, rivers, and oceans. Volcanoes exhale carbon dioxide from Earth's interior. Weathering on land inhales it, grain by grain. When warm, rains fall harder, plants and microbes work faster, and chemical reactions nibble at fresh rock, tucking CO2 into bicarbonate that rivers carry to the sea, where it becomes carbonates, limestone, dolostone, locked away for ages. Warmth speeds the broom, and the broom cools the room. When cold, the broom slows, weathering eases, volcanic breath gathers, CO2 rises, warmth returns, its negative feedback written in riverbeds. Snowball Earth is what happens when the thermostat gets pushed to an extreme. Before the freeze, tropical continents wore fresh, dark rock. Monsoon rains scrubbed CO2 eagerly, nudging global temperatures down. As ice spread and brightened the planet, cold suppressed the very reactions that would normally push back. Under a hard lid of ice, rivers dwindled, soils slept, and the atmosphere could no longer launder volcanic carbon well. The thermostat was still there, but its lever was stuck. Outgassing continued. Removal stalled. Slowly, the greenhouse thickened until, at last, warmth won and the ice relented. After the break, the same thermostat snapped the other way. A hot, wet world greeted raw, freshly scoured continents. Weathering roared back to life, routing CO2 into rivers at a furious pace. Oceans became oversupplied with the ingredients for carbonate minerals, and they laid down that pale cap, the chalky curtain draped directly over glacial rubble. In a sense, cap carbonates are the thermostat's signature, proof of a surge in weathering and a sea ready to turn dissolved carbon into stone. Geologists can trace the workings of this system with delicate needles and patient eyes. Old soils, paleosols, preserve minerals that tell of past weathering intensity. Ratios of strontium isotopes in marine carbonates whisper how much continental crust was being washed to sea. Carbon isotopes sketch the push and pull between organic burial and carbonate deposition. None of these records is a loudspeaker. Together, they're a chorus that fits the outline we've been following. Drawdown before the freeze, accumulation during it, rush and rebalancing after. There is comfort in this rhythm. It says the planet has long-term ways of finding center, even if it wanders. That doesn't make climate tame on human timescales. The thermostat's dial moves in millions of years, not decades. But for our story, it explains how a mirror-bright world could both arrive and depart without magic. Only rock, water, air, and time. Stand for a moment on a cryogenian hillside in your mind. The rock is dark and newly exposed, the rain warm and slightly acidic, the streams milky with ions on their way to the sea. Each droplet is a messenger, carrying carbon toward stone. Far offshore, tiny crystals begin to grow, blanketing the seafloor in soft white. The thermostat is working again, and in its steadying hum, life will find room to try new shapes. When climates turn pages, the ink they use is isotopes, tiny weight differences inside familiar elements that behave just a little differently. After Snowball Earth, those subtle weights wrote exuberant signatures into muds and carbonates, giving us a chemical diary of the thaw. Begin with carbon. In the quiet before the freeze, marine carbonates often carry a modestly heavy carbon signal, slightly enriched in the heavier isotope, 13C, because life was busy tucking lighter 12C into organic matter that sank away. But at the top of glacial layers, right where cap carbonates bloom, that story flips. The carbonate's carbon often swings light, a negative D13C excursion. It's as if the ocean took a deep gulp of 12C-rich carbon from rapid weathering, volcanic outgassing, and the sudden remineralization of organic matter flushed in by the melt. The cap records this rush, not slowly, but in a single bright, chalky breath. Now listen to strontium, an element that sneaks into carbonates and tracks the balance between fresh continental crust and older recycled rocks. Its isotopic ratio, 87SR, 86SR, tends to rise when rivers are chewing on continents, delivering the fingerprints of weathered granites to the sea. After the thaw, those ratios tilt upward, another hint that rainstorms on raw, post-glacial landscapes were vigorous, and that rivers were busy hauling the continents to the shelf grain by grain. Sulfur adds a moody harmony. In oxygen-poor oceans, microbes can drive sulfur isotope patterns into extremes, leaving pyrite, fool's gold, with distinctive signals. As oxygen worked its way back into surface and shelf waters, those extremes softened. It's like hearing a piece of music modulate into a key with more light, still complex, but less constrained by darkness. In a few basins, barite, barium sulfate layers appear just above glacial beds, marking pulses of sulfate delivery to the sea as weathering and circulation reawakened. Even oxygen, inside the water molecule itself, whispers about temperature and ice volume. Ratios in certain minerals shift as climates warm, a quiet nod that the planet's white coat was thinning, lakes and shallow seas warming enough for chemistry to move quickly again. None of these measures alone is a trumpet. Together, they form a chamber orchestra playing the same theme: rapid deglaciation, roaring weathering, lively circulation, and a sea newly ready to host ambition. What I love about these fingerprints is their humility. They are not fossils with faces. They are not boulders with scratches. They're numbers, small tilts in weight and preference. Yet through them, we glimpse an ocean changing its mind, an atmosphere loosening its grip, a crust rinsed clean and set back into the cycle. The cap carbonates are the canvas. The isotopes are the brush strokes that let us see motion. Hold a thin slice of that pale rock up to the light in your imagination. It looks uniform, almost blank. But in the lattice of its minerals, those tiny weightings hum. They carry the memory of rain on new stone, rivers milky with ions, waves over shelves rich with bloom. They tell us the thaw was real, and that it arrived like the lifting of a veil. When the mirror of ice finally lowered, and the seas learned to breathe again, the shoreline changed its voice. Sunlight reached shallow banks long starved of day. Waves combed microbial carpets that had waited in the hush. In this gentler world, bodies began to try new shapes. No shells yet, no claws, only softness learning to hold itself together. We call this chapter the Ediacaran, the first period in Earth's history named for life we can still trace with our hands. Walk quietly across a tidal flat in your mind. Under the skin of water, microbial mats quilt the sediment, sticky films that bind sand and silt, turning the seafloor into a living blanket. On this soft foundation, creatures rise like fronds from a dream, leaf-shaped, ribbed, anchored by a holdfast, quilted ovals pressed into the mat, coils and discs that look like punctuation in a language we're always just about to read. They are not plants. They are not animals as we recognize them. They are experiments, tissues organized into surfaces that could gather light, catch dissolved food, or trade gases more efficiently than scattered cells ever could. Why here? Why now? Oxygen helps. After the thaw, winds and waves mixed the surface ocean. Rivers delivered nutrients. Blooms came and went, and oxygen reached farther into shelf waters. With more oxygen, cells could afford costlier choices. Collagen to stitch tissues, signaling molecules to coordinate. Energy budgets big enough for bodies to get larger without losing their way. The sea didn't turn into a carnival overnight. Evolution moves on the patience of generations. But the constraints loosened. Options multiplied. Notice what you don't see. There are few deep bite marks, few signs of hard parts scraping or crushing. This is a mostly peaceful horizon, a world before jaws. Many forms lie still, pressing their bodies into the mat beneath them, perhaps feeding by absorbing dissolved organics or hosting microbes on their surfaces. Traces appear here and there, wiggles and trails that could be the hesitant paths of early burrowers. But for the most part, the sediment stays undisturbed, like snow no feet have crossed. If the cap carbonates were the ocean's bright curtain call after the freeze, these soft-bodied communities are the opening scene of a quieter play. They suggest a lesson we keep meeting in this story. Extreme change can prune, but it also prepares. The snowball didn't create complexity by itself, but the way it ended. Nutrients flushing from raw continents, oxygen pulsing into shallow seas, chemistry shifting toward possibility, set a table where complexity could sit down and try ideas. Hold one of those quilted impressions in your imagination. It looks delicate, and it was. Yet it represents a threshold crossed, a body held together by more than hope, drawing energy from a world that had learned to breathe again. The night of ice is over. The light is not yet loud. This is the hush before footsteps. When ice let go, the continents were raw, fresh faces of rock lifted to rain. Every storm was a hand on sandpaper, every river a fast conveyor belt carrying the fine meal of mountains to the sea. In that milky water rode a quiet revolution: phosphorus, iron, silica, nutrients that life had been rationing for an age. Imagine a shelf sea under a warmer sky, the cap carbonates just beginning to settle like pale dust. River plumes bloom outward, green fans unfurling in the sunlight. Microscopic drifters wake in waves, turning light and nutrients into soft carbon snow. It rises quickly, like an April that forgets to end, then sinks as flakes and threads, feeding bacteria, feeding sediments, writing thin, dark lines into mud. Each pulse leaves the water clearer, then the next storm blurs it again. The ocean learns a new heartbeat: feast, fade, rest. But feasts have shadows. When too much organic snow falls too fast, bacteria chew through oxygen in the quiet layers below. Waters turn breathless. Iron and other metals slip back into solution. In the far corners of basins, purple and green sulfide-loving microbes may take the night shift. For a while, the sea can be both generous and strained, oxygen-rich at the top, starved beneath, its chemistry tilting between promise and burden with each flood, each wind, each overturn of seasons that were still finding themselves. This dance doesn't cancel the larger trend. It complicates it in a way living systems often do. On average, more oxygen skims the surface and reaches the shelves than during the long freeze. On average, nutrients keep arriving from land, seeding productivity and building the habit of burying carbon, a slow, planetary way of banking oxygen for later. Yet locally, and sometimes dramatically, the feast draws down breath faster than wind can replace it. The sea becomes a patchwork, bright shallows that sparkle with life beside deeper tongues that doze in low light. From the shoreline, you'd sense only the bright part. Water the color of spring tea, a soft haze of plankton just beneath, a scent of salt and something green. Fish had not yet learned these waters. Shells were only an idea forming in the chemistry of bodies. But the stage crew was busy. Phosphorus budgets rising and falling, iron shuttles switching direction with each redox flip. Tiny molecules of oxygen making new friends in tissues that were beginning to dream of muscles. With time, the frenzy cools into rhythm. Weathering eases as soils take hold. Rivers learn their banks. Blooms grow less explosive, more dependable. The ocean's mixed layer extends and relaxes with storm and season. The dark layers below keep their mysteries but give up less ground. In that steadier world, cells can invest. Scaffolds of collagen, conversations between tissues, quiet experiments with moving through sediment rather than lying on top of it. Hold the picture. A world fresh from famine, learning how not to overshoot. The memory of ice lingers in bright rocks. The promise of bodies is written in the way rivers now speak to the sea. Feasts teach limits as well as possibilities, and in that lesson, complexity finds room to grow. To feel how global this story was, let's walk quietly through the places where the ice left its autograph. Each stop is a whisper from the same winter. Begin in Namibia, where desert light falls on cliffs of dark diamictite. Pebbles and boulders float inside like stars in night glass, a jumble only ice can make. Lay your palm on the surface and you'll feel polished planes and faint grooves, scratches the width of a thumb, aligned as if a giant comb passed over the rock. Above, the color flips suddenly to pale cream, cap carbonates draped smooth as frost, cold pressed against warm, stone against stone, with almost no pause between. Cross quietly to South Australia. In the Flinders Ranges, tilted layers step across the landscape like the ribs of a sleeping animal. Here, too, unsorted glacial debris gives way to bright carbonates. In some outcrops, needle-like crystals once grew as fans, now preserved as ghosts in the rock. Mineral fireworks frozen mid-bloom. Evidence of seas so supersaturated after the thaw that they hurried to turn dissolved carbon into stone. Now to China, along the edges of the Yangtze platform. The sequence repeats. Low-latitude glacial deposits, then caps. In some beds, lonely dropstones pierce fine laminations, rounded rocks that fell from melting ice into quiet water, puncturing the seafloor's delicate layers like commas in a careful sentence. Above them, the pale curtain again. The rhythm is patient, insistent. Slip north to Arctic Canada and the Mackenzie Mountains. Here, ancient seafloors have been lifted into the sky, their stories stacked where wind can read them. Glacial pavements show striations, parallel cuts that tell you the direction ice once flowed. Like old wagon ruts through a pass, they point the way the glacier moved, engraving memory directly into bedrock. Each region carries local color, different basins, different minerals, different pauses, but the melody is the same. Ice at latitudes that should have been warm. A rapid deglaciation. Seas laying down bright carbonates in the first flush of warmth and weathering. Even the chemistry agrees, in quiet numbers. Carbon isotopes tipping light at the cap. Strontium leaning toward the signature of freshly weathered continents. Occasional bands of rust that speak of oxygen returning to surface waters. What I love about this tour is its consistency across distance. You can stand in Namibian sun, Australian heat, Chinese haze, Canadian chill, and touch the same chapter. Continents that now sit oceans apart were once neighbors, their matching pages slot together like a puzzle finally solved. Paleomagnetism adds its compass, tiny iron grains frozen in their ancient orientation. Tell us many of these glacial deposits formed near the equator. Tropical ice. The phrase still tastes improbable, even as the evidence sits quiet and solid beneath your fingers. Take a breath and look back along the path we've walked. The repetition is the point. Nature rarely gives us exact copies, but here the rhyme is strong enough to carry across a planet. Freeze, then flourish. Darkness, then a pale blaze of carbonate. Constraint, then the first drafts of complexity. Snowball Earth was not a local storm. It was a world state, written on cliffs from desert to tundra. Freezing a planet is easier than unfreezing it. That's the quiet trick behind Snowball Earth, a property physicists call hysteresis, the idea that the path into a state and the path out of it are not the same road. Once bright ice had pushed far enough toward the equator, reflection fed on itself. More white meant more sunlight bounced away, which meant more cold, which meant more white. To reverse that loop, the planet needed more than a nudge. It needed a shove. Volcanoes supplied it, one breath at a time. With rivers and soils idled beneath ice, carbon dioxide had nowhere to go but up. Over long, quiet centuries, the atmosphere thickened with a greenhouse gas that is weak in a day and strong across a million midnights. Models suggest you need orders of magnitude more CO2 than today to pry open a snowball, enough to turn infrared escape into a slow drip and let warmth pool near the surface. No single plume did the job. The sum did. Still, even a thick blanket of CO2 faced a mirror. That's where small patches mattered. Dust and ash darkened the ice in places. Winds opened narrow polinias. Summer light near the equator, faint but faithful, carved blue melt ponds. Each one drank more heat than it reflected. Meltwater smoothed rough snow into glassy surfaces that absorbed yet more sun. What once amplified freezing began, inch by patient inch, to amplify thaw. Water vapor joined the rescue. As soon as air could hold a little more moisture, that moisture trapped additional heat, strengthening the greenhouse and fattening clouds that, paradoxically, sometimes warmed more than they cooled, especially over darkening, newly wet surfaces. A different feedback loop spun up. Melt, vapor, warmth, more melt. Beneath the thinning lid, currents stirred as fresh, light water feathered the surface. Crevasses widened, bergs calved, coastlines shifted from blue-white cliff to gray, dripping shelves. Hysteresis makes the escape feel sudden when it finally arrives. For ages, not much seems to change. Then a threshold gives, and the system races downhill. Melt ponds connect into lanes, lanes into seas. The sky, long starved of humidity, thickens. Snow turns to sleet, sleet to rain. Rivers wake with a roar, gnawing young valleys into raw rock. It's not a tidy, even thaw, no global switch flips in a single season. But the direction is clear, and the pace, once set, is brisk in geologic terms. There's a lesson here that outlives the cryogenian. Climate can be stable in more than one configuration. A world can sit comfortably in a cold state or a warm one, and the shove required to move between them can be larger than the small gusts that keep weather dancing day to day. On Snowball Earth, the shove out was volcanoes, dust, sun angles, and time, always time, working together until the mirror cracked. Hold that in your palm for a moment. The patience of processes, the suddenness of thresholds. Then listen. The first warm rain is beginning to tap on ancient ice. Picture the planet as a single shining mirror, ice from pole to pole. Now lean closer, and you'll see it isn't flawless. Wind and tide pry narrow seams, cracks where dark water blinks through like eyes opening in sleep. These are polinias and leads, the breathing holes of a frozen ocean, and they mattered more than their smallness suggests. Along coasts and over submarine ridges, currents press upward. Tides flex the crust. Storms worry the ice until it yields a lane a few meters wide, then tens, then a gray patch that refuses to freeze as quickly as the calm around it. In the brief, faithful light near the equator, those windows drink sunlight instead of reflecting it. They make heat locally, melt a little more, and let the ocean exhale and inhale with the sky. Oxygen slips in, carbon dioxide slips out. The surface layers stir. Life waits for moments like that. Microbes that spent long, dark months clinging to brine channels wake and bloom along the edge of open water, turning thin sunlight into sugar and a trace of oxygen. Tiny cells skate the boundary, where cold and light meet, where nutrients well upward from beneath the lid. Each lead becomes a moving oasis, drifting with wind, leaving behind a faint trail of chemistry like the wake of a boat on a dawn lake. Polynias are also corridors, nutrients that piled up in the dim interior, iron, nitrate, phosphate, leak upward when the surface opens, seeding new growth and helping the ocean trade its stale breath for fresh. In this way, small patches stitch together a larger habitability, like lanterns strung across a long night path. Even if the ice elsewhere is thick and snow-pale, these dark eyes keep the system from sealing completely. Feedbacks take note. A ribbon of open water absorbs more sunlight than the white beside it, warms a little, widens a little. Melt ponds flower on nearby ice, connected by thin threads that grow into lanes, and the lanes into partial seas. It's not a uniform thaw. It's stippled, then mottled, then marbled. Change beginning at the margins and seams, where it often begins in nature. Stand in your mind on the edge of one of those leads. The air is knife cold, but smells faintly of salt and wet stone. The water is inky, almost metallic, whispering against the ice like silk. Under the surface, green wakes in the first meters, a veil of cells catching photons and making a little more room for breath. Far below, slower currents carry the news outward. There is exchange again. This is how a frozen world keeps its options open, not by tearing the roof away in a single moment, but by prying it up in slivers and letting day sneak in. Seams in the mirror, lifeboats on a global sea. A frozen planet is not a solid silence. Press your ear to the base of a glacier, and you'll hear it. A low, traveling murmur, like water speaking through teeth. Even at far below freezing air temperatures, pressure and geothermal warmth can coax ice to melt where it hugs the ground. There, in the dark, a secret plumbing wakes, thin films that slide across bedrock, threads joining into rills, rills folding into braided rivers that run black and fast beneath a roof of blue glass. These rivers don't meander the way summer streams do. They surge in pulses as overlying ice flexes and creaks, as melt pockets connect, as channels clog with ground-up rock and then blow clean again. The water is heavy with rock flour, a fine powder made by the glacier's grinding gait. Each drop is clouded with minerals, ready to feed the ocean the moment it reaches the light. In places where the ice thins near the coast, those subglacial rivers burst into the sea as turbid plumes, cold, dense, and rich, seeding shelves with nutrients even before the great thaw. Above the rivers, the ice itself is busy. Imagine a slow-motion factory floor. The base shears, the middle flows, the top creaks and winters. Rocks frozen into the soul of the glacier carve long, parallel grooves into bedrock, striations that point, like compass needles, in the direction of ancient flow. Where the water finds persistent paths, it can lay sandy ridges in tunnels under the ice, features that long after melting stand as sinuous hills across open country, eskers like signatures left by vanished pipes. Not all subglacial rooms are thin. Some broaden into lakes, pools held in bedrock hollows, warmed from below by Earth's steady heat. In the cryogenian, such lakes would have been common wherever the ice was thick, but the crust beneath was a little warmer, near rifts, above hot rocks, along mountain routes. In their black water, chemistry could simmer for centuries. Iron, silica, dissolved gases accumulating, microbes trading energy without a single ray of sun. When an outburst flood finally punched through, it would carry that concentrated brew out to the margins, a dark tonic poured into newborn seas. These hidden hydraulics mattered. They lubricated the ice, setting its pace. They sculpted landscapes, valleys over-deepened by pressurized water, rock knobs polished to a shine, packets of sand stacked and sorted in rhythmic layers. They also kept a trickle of exchange alive when the surface world felt sealed, nutrients moving from crushed rock toward the ocean, warmth licking upward where the crust ran hot, little local breaths in a climate holding itself still. Close your eyes and let the picture settle. A roof of ice, cold and radiant. Below it, a map of shadowed water, traced by pressure and stone. You can hear the soft grind, the hiss of a tunnel widening, the sudden hush when a channel collapses and the river finds a new way through. Even here, in the tight fist of deep freeze, the planet keeps moving fluids from where they are to where they are needed. It's a quiet promise that connection persists, even when the surface forgets. Even in a planet of light, there are specks of night. Picture winds carving across bare, glacial plains. No forests to hold the soil. No grasses to hush the gusts. Just open miles of ground-up rock. The air lifts that fine powder and carries it far, a veil of dust moving over the ice like a quiet weather. Volcanoes add their own handwriting, ash falling in soft drifts after distant sighs, peppering the bright surface with gray. On a world ruled by reflection, these flecks matter. Clean snow is a mirror. Dirty snow is a sponge. A patchwork of dark grains lowers the albedo, an artist's term for brightness. So sun that once bounced back to space now sinks in, warming a little pool, then a lane, then a sheet. Meltwater beads, slides and gathers, polishing the surface into glass that drinks even more light. In shallow hollows where dust collects, cryoconite forms, little pockets of ink-blue meltwater with a pinch of life inside. Each tiny pond becomes both lens and hearth, focusing sunlight and feeding microbes that make the world just that much darker still. The effect is small in any one place, but the planet listens to small things repeated. Dust didn't simply warm, it fertilized. Iron within those fine grains is a micronutrient that many photosynthetic microbes crave. When winds shove powdered rock across the ice and into narrow leads, that iron dissolves like a spoonful of tonic in tea. Along the margins where open water persists, plankton wake a bit brighter, bloom a bit more, and send a bit more organic snow downward, a pulse that in time helps oxygen linger in the surface ocean and gently tugs the carbon cycle toward change. Volcanic ash played both sides. High in the atmosphere, sulfate aerosols from eruptions can cool sunlight for a season or two, drawing a gray curtain that chills the day. But what falls out onto the snow below works in the other direction, darkening the mirror, quickening the melt. Add heat from the vent fields beneath, and you get a subtle braid of influences. A short, high chill above, a long, low warm below, and across the wide white in between, a steady drift of grit tipping surface physics toward thaw. Listen to the texture of it. The hiss of wind lifting flour-fine grains, the tick of ash on ice, the soft pop when a cryoconite hole breaks through and starts a trickle. None of this rips the roof off the ocean in a single afternoon. But it doesn't need to. Feedbacks are patient machines. Darken a surface, invite a melt pond. The pond smooths, drinks more sun, widens. Its edges calve into nearby shadows. Separate ponds connect. By the time the greenhouse sky has thickened enough to press warmth against the mirror is already spidered with seams, ready to yield. Hold the image of a white world salted with gray, every grain a vote for change. In the grand accounting of ice and light, dust and ash were small accountants, quiet, meticulous, and over time decisive. After a million winters, the first warm storm must have sounded impossible, soft at first, then certain, then loud. The air, newly able to hold water, thickened with cloud. Drops found each other and fell on rock so fresh it still smelled like the inside of earth. Petrichor without plants. Just rain on raw basalt, on granite shaved clean by ice, on slopes with no roots to hold them. Water is a sculptor that works fastest on new stone. Rivulets braided into torrents, torrents into rivers, fanning milky with ground-up minerals. Nick points, sudden steps, migrated upstream as channels carved down, changing the music of the landscape from hiss to rush to roar. Valleys that glaciers had overdeepened now found outlets. Cataracts unstitched ancient ice-dammed lakes. Sheets of water leapt across ledges, carrying boulders like beads. Where floods met the newborn sea, their weight and speed drove dense, sediment-laden plumes down the continental slope, laying broad, quiet fans on the deep, submarine deltas written in sand and silt. Each storm was chemistry in motion. Warm rain, faintly acidic with CO2, licked ions from fresh surfaces, calcium, magnesium, bicarbonate, then hurried them seaward. The ocean, shocked and overfull, answered by growing mineral snow, those pale cap carbonates frosting the shelves. Between tempests, sunshine soaked into dark, wet ground and quickened weathering further. The planet's stone thermostat, jammed during the freeze, was now turning smoothly, pulling greenhouse gas from the sky and slipping it into rock. Sea level, too, found a new voice, first rising as continental ice collapsed, then wobbling as land, freed of its burden, sprang back in slow, elastic breaths. Coasts walked inland and back again. Estuaries formed overnight in geologic terms, deepening with each tide. On wave-washed flats, microbial carpets stitched sediment against the pull of water, quilting surfaces where the first soft-bodied experiments of the Ediacaran would soon lie. The storms did not arrive as chaos. They arrived as a lesson. Downpours taught slopes how to give way and then how to hold. Gullies widened, then grew banks and bars. Fans found their angles and persisted. Rivers learned to meander once their fury eased, curling through valleys the ice had left too straight. In that easing, the world exchanged violence for habit. Nutrients pulsed, then patterned. Oxygen spikes smoothed into a steadier tide along the shelves. Between rains, quiet returned, the kind of quiet where bodies can plan. Stand with me for a moment, beneath that first long shower. The sound on stone is round and bright. The smell is metal and slate. Mist rises in veils from black ledges. You can feel the planet lowering its shoulders. What the ice had simplified, the rain complicates, happily. Pathways multiply, cycles restart. The stage is almost set for creatures to step forward and ask, gently at first, what else a body might do. For a long time, the sea had been a library sealed in glass, pages of water stacked but rarely turned. Under the snowball lid, surface brine sank in slow, salty fingers. Deeper layers moved like a sleepwalker, careful and quiet. When warmth returned, someone opened the windows. Wind put its hand on the surface and ruffled it. Fresh meltwater feathered the top into lighter sheets. Sunlight drew gentle breezes into storms, and the ocean, patient as a heart that has waited, found its beat again. Circulation is the sea's memory. Where water cools and grows salty, it sinks. Where it warms or freshens, it rises. During the freeze, that grammar was muted by ice. Now, with the lid cracking and the sky remembering rain, sentences could be spoken again. Downwelling at new coasts, upwelling where winds pulled surface waters apart, gyres knitting basins together. Picture blue highways waking, broad currents running along shelf edges, narrow jets slipping through newborn straits, slow rivers of deep water returning nutrients to the light. With motion came exchange. Gases traded places more easily. Oxygen working its way into the mixed layer and farther down the slope. Carbon dioxide finding both escape to the air and storage in waters that would not surface for years. Trace metals, tiny but decisive, entered the dance. Iron dust, washed and blown from raw continents, tipped blooms into brilliance along upwelling margins. Molybdenum and copper, carried by rivers, helped enzymes that fix nitrogen and split oxygen do their jobs a little better. The chemistry that had been a constraint became, piece by piece, a scaffold. Not every corner exhaled at once. Freshwater caps could stall sinking. Eddies could fence off pockets of breathless deep. But the averages shifted. Seasonal overturn began to reach into shelves that had been starved. Internal waves, silent underwater tides, dragged cold, nutrient-rich water upward along continental slopes, feeding plankton in ribbons that curled like handwriting across the sea. Each bloom pressed a little more carbon into mud. Each quiet, oxygenated summer set the table for bodies to try more expensive plans. Listen for the textures of this new pulse. The drum of surf where there had been a cliff of ice. The low rush of a boundary current turning a cape. The faint fizz when storm-roughened water drinks the sky. If you could ride a grain of plankton from the surface to the dim and back, you would feel the elevator move. Down with the weight of your own bloom. Up with the tug of wind months later, back into light you can use. This is how complexity wins time. A breathing ocean smooths the spikes of feast and famine. It spreads fortune from a wet river mouth to a clear mid-shelf, from a dusty afternoon to a week of soft green water. In that steadier pulse, cells can grow larger without starving. Tissues can coordinate without suffocating. And the first timid steps into movement, burrowing, gliding, folding, can be paid for with oxygen in the bank. Hold the map of those waking currents in your mind. Arrows looping, diving, rising. The world hasn't forgotten the cold. The rocks still carry it. But the sea now moves like a living thing again, and in its rhythm, possibility expands. After the ice let go and the seas found their pulse, the atmosphere began a quieter change you can't see, but you can feel, like a room being aired out. Oxygen, already present from much earlier ages, rose again in steps, as if the planet took a deeper breath and decided to keep it. Geologists give this hush a name: the Neoproterozoic oxygenation, a long exhale that loosened constraints on bodies and plans. You can hear it in subtle instruments. Trace metals that prefer oxygen, molybdenum, uranium, grew more common in certain marine shales, a hint that the surface ocean was staying oxygenated longer and more often. Chromium isotopes shifted in ways that suggest stronger oxidative weathering on land. raindrops and streams carrying a brighter chemical signature to the sea. Even tiny iodine fingerprints in carbonates whisper of shallow waters where oxygen lingered. None of these is a shout. Together they hum the same tune. More breath above the shelves, more often. Why now? Partly, the feasts after the thaw learned rhythm. Instead of violent booms that gulped oxygen, blooms became steadier, and more of their carbon was buried for keeps in mud, leaving O2 to idle in air and water. Partly, rivers kept a measured flow of nutrients to coasts, feeding photosynthesis without constantly tipping basins into breathlessness. And partly, the moving ocean spread good fortune, upwelling in the right places, overturning at the right seasons, so oxygenated water traveled rather than stalling. Oxygen is expensive to make and precious to keep. With a bit more of it, cells could afford richer chemistries, stronger collagen to stitch tissues, more elaborate signaling to orchestrate growth, mitochondria running a little hotter, harvesting more energy from each bite. Size could increase without suffocation. Shapes could grow thicker without their middles going dim. In this airier world, the Ediacaran's quilted forms make sense. Soft bodies experimenting with surface area, gas exchange, and gentle movement over or within microbial mats. The rise wasn't uniform or forever upward. Deep basins still slumped into low oxygen spells. Shelves sometimes winked breathless beneath heavy rains of organic snow. The planet was learning balance, not perfection. But the averages changed, and averages matter over evolutionary time. A few millimeters more of reliably oxygenated water, a few weeks more of mixed layers each year. Those tiny margins are where complexity buys its tickets. Stand at the edge of that ancient sea in your mind. The water is a softer blue now, the kind that lets light reach farther before it dims. In the top few meters, plankton stitch sunlight into sugar with a confidence they didn't have before. Below them, oxygen holds on long enough for detritus to be processed without the whole system gasping. On the seafloor, a thin skin ripples where something has begun to move within the sediment rather than merely rest upon it. The first hint that the substrate is becoming a place to explore, not just a sheet to lie on. This is the quiet arithmetic of breath. Not a revolution in a day, but a rebudgeting that opens possibilities. The snowball's end didn't write the future by itself. It made a promise, and oxygen kept it. After the ice stepped back and the ocean began to breathe, the water turned faintly velvet, rich enough in oxygen for bolder chemistries. In that softer blue, some of the earliest animal-grade plans may have stirred. Nothing with teeth or armor, just bodies built like sieves, letting water do the work. Picture a sponge the size of your palm, a chimney of living pores. It doesn't chase, it sifts. It doesn't shout, it hums. The rocks don't hand us a clear photograph. Instead, they offer molecular hints, biomarkers, the waxy remains of ancient lipids that survive inside stone like scents in old fabric. Some of these chemical fossils have been interpreted as traces from demosponges, suggesting that simple filter feeders were already tasting the post-snowball sea. But science is careful. Other researchers note that certain algae can make similar molecules. The signal might be sponge, or it might be seaweed. Either way, the ocean was busy enough to support organisms experimenting with multicellularity and gentle metabolism. There are shapes, too. Tiny, exquisite puzzles in Ediacaran rocks. In China's Wengan deposits, mineralized microfossils show cell clusters that look like early embryos or simple animal-grade tissues. Are they truly animals? The debate continues, but the theme is steady. After the long freeze, bodies tried more ambitious blueprints. Oxygen helped, nutrients helped, moving water helped most of all. A sponge's life is a love letter to circulation, pumping liters upon liters through itself each day, sampling what the sea provides, returning it a little cleaner and a little changed. Imagine that quiet architecture at shelf depth. Pillars and low domes of porous flesh perched on microbial carpets. Curtains of tiny chambers where cilia beat in synchronized waves. Every beat is an energy bet that only works when oxygen lingers and food arrives steadily. Snowball's end made both more likely. Upwelling tugged nutrients to the light. Rivers signed a long treaty with the sea. The mixed layer learned a new, dependable pulse. In that cadence, even modest animals can afford to exist. Why does a sponge matter in a story that will soon host fronds, frills, and later jaws? Because filters change worlds. They clarify water, recycle particles, stitch microbial and macroscopic life together. They're civil engineers for clarity. Once a coastline hosts millions of small pumps, light penetrates a bit farther. Microbial mats shift their balance, and the whole fabric of the seafloor begins to reorganize. Complexity often starts with housekeeping. Hold that image. A low reef of soft chimneys in green-blue water, each one a tiny cathedral of flow. No drama, no chase, just quiet persistence, the kind that makes later noise possible. Whether the first of these truly wore the name animal yet, or something close by on the family tree, the ocean was clearly ready for them. Before shells and spines, there were intentions pressed into mud. On Ediacaran seafloors, those quilted microbial mats that held the sediment together. Something began to move, first as hesitant wiggles, then as purposeful trails. These are trace fossils, not bodies but behaviors. Shallow grooves where an animal nudged along the interface. Tiny furrows where it pushed aside grains to taste what lay below. They are whispers of nerves organizing, muscles negotiating with resistance, bodies learning that the world is not only a surface to lie upon, but a place to explore. Why then? Oxygen helps you pay the metabolic cost of movement. Nutrients arriving in pulses make it worthwhile to search. And mats themselves encourage curiosity. They trap organic matter in thin layers, so a creature that can sense and follow gradients finds dinner by drawing a line across the seafloor. Each faint trail is a contract, energy spent for energy earned, and that arithmetic only works in waters that keep their breath long enough for the trip. With motion comes depth. The first shallow burrows appear, little U's and J's, evidence that a body could now push into sediment and come back out again. Even a centimeter matters. It tests symmetry, coordination, and a new kind of map in the mind. The substrate changes in response. Once stable mats are rucked and pilled, oxygen trickles a little deeper, microbes rearrange. The seafloor becomes an ecosystem with layers, not just a sheet. Imagine kneeling by that ancient flat, your palm on cool, rippled stone. A thin groove curves, stops, doubles back. At its end, a small dimple, perhaps a pause, perhaps a bite. There is no shell to admire, no spine to measure, only a decision made hundreds of millions of years ago and recorded in silt. In a quiet way, it's a revolution. A world that had been largely two-dimensional is testing the third. Hold that line in your mind. Simple, tentative, enough. From such lines, paths. From paths, habits. From habits, the confidence to build bodies that can go farther. Soft bodies are quick to change, but soft also invites teeth. Near the close of the Ediacaran and into the earliest Cambrian, the rock record sprouts hard whispers, tiny tubes, plates, spicules, the small shelly fossils. Their names are many and delicate. Cloudina's stacked paper-thin funnels, tubular dwellings like rolled parchment, bits of armor no bigger than a grain of rice. They are not grand fortresses, they are first steps toward edges that hold. Minerals offer options. Calcium carbonate is common in seawater after the Cap Carbonate surge. Silica is available where vent-rich fluids leak or where rivers supply it faithfully. Bodies learn to guide those ions onto scaffolds, precipitating crystals along organic templates, biomineralization as controlled weathering. A collagen skin gains grit, a tube gains stiffness, a surface sprinkles spines that change the conversation with the outside world. Why add hardness? For anchoring, for channeling water, for defending. A tube lets a soft feeder sit a few millimeters taller into better flow. A rind discourages a grazer from turning you into paste. Even if true predators were rare, the mere possibility reshapes plans. When bites pay, armors sell. The sediment records the consequences. Mat grounds, once smooth, show more disturbance. Little borings pierce Cloudina's walls, a suggestion that trial teeth were present, testing the new materials. Hard parts also echo. When many filters and grazers stiffen their edges, water clears, light sharpens. Mats thin in places and flourish in others. Ecosystems become mosaics, not blankets. The stage is set for feedbacks that favor building and moving. Better clarity helps sight evolve. Stiffer bodies can push sediment aside with leverage soft flesh can't muster. None of this is a jump. It's a drift that speeds, a slope gaining grade. Picture a shallow shelf in soft morning light. Low, calcified chimneys dotting a plain, each housing a tenant that sifts the passing day. Between them, trails stitch the sediment. Above them, the water carries more oxygen than it used to, enough to fund experiments. The toolkit has a new tool, and even small tools change what a hand can make. By the time the calendar turns to the Cambrian, 1 million years ago, the quiet rehearsal swells. Body plans diversify. Segmented trunks with jointed legs, frilled swimmers with grasping limbs, spiny, armored forms that look like ideas made gleefully literal. Trilobites scuttle across the seafloor in polished ranks. Early arthropods prowl the water column. Burrows deepen and branch like roots. It is not an explosion in a single sunrise, but it feels like one on the page. Many fundamental blueprints appearing in a geologically brief span. Snowball. Earth is not a prologue you can skip here. The way it ended matters. Oxygen that lingers, nutrients that pulse within bounds. Oceans that mix on a schedule robust enough to spread opportunity but gentle enough to avoid constant suffocation. Hard parts, seed arms races, faster pursuers, better shields, keener senses. Eyes refine in clarified water. Muscles strengthen in bodies that can afford their upkeep. Guts experiment with length and complexity as diets diversify. The seafloor, once ruled by mats, is now riddled with galleries where animals live within the sediment. Ecosystem engineering is underway. Yet humility belongs in this chorus. Not everywhere saw the same pace. Basins differed. Shelves blinked in and out with sea level. Extinction trimmed some experiments even as others grew ornate. What holds across the map is the sense of constraint lifted. The snowball's lessons about thresholds, feedbacks, and the power of oxygen to underwrite ambition echo as bodies compose. Stand at the edge of that Cambrian sea in your mind. The sound is busier. Rasp of limbs on sand. Faint thrum of swimmers above. The soft collapse of a burrow roof as its tenant shoulders past. This is what overture means here. Themes introduced that the rest of animal life will vary, elaborate, and reprise for 500 million years. Snowball Earth is stitched from patient work. In deserts, mountains, and road cuts, geologists trace sequences, glacial diamictites overlain sharply by pale cap carbonates, repeated across continents. They map striations, parallel scratches on bedrock that mark ice flow. They find dropstones punched through fine laminations, lonely commas in quiet mud. Each site is a syllable. Together they speak fluently. To time the chapters we lean on tiny clocks, volcanic ash layers, thin gray bookmarks, host zircons that record uranium's slow decay to lead. UPB dating reads those grains with laser light and mass spectrometers, bracketing when a basin filled and when ice withdrew. Paleomagnetism adds geography. Iron minerals lock in Earth's magnetic field as sediments settle or lava cools. Measured today, those directions tell us where the rocks were relative to the equator, making the case that glaciers reached the tropics. Geochemistry colors the outlines. Carbon isotopes swing negative at the cap. Strontium ratios rise with vigorous post-glacial weathering. Sulfur and iodine signatures hint at how oxygen returned to shelves. Iron formation rusts reappear in places, suggesting deep waters that once again met oxygen at their tops. None of these measurements shouts alone. Together, they settle arguments well enough to move on to the next questions. Finally, models test plausibility. Climate simulators, numerical worlds run on supercomputers, check whether ice can grow from poles to low latitudes under certain CO2 levels, reflectivities, and continental positions. Whether you can thaw with volcanic outgassing alone, how dust, water vapor, and clouds alter the march. When models and rocks agree, confidence rises. When they don't, we go back to the field, the lab, or the code and ask better questions. It's an ensemble art. Boots, hammers, microscopes, beams, and bites. And it's ongoing, which means edges blur and debates stay alive. Snowball versus slushball. Single global lids versus mosaics of thickness. The exact timing and pacing of the thaw. Science here is less about final pronouncements than about sharpening a picture until the remaining fuzziness is where the real mysteries live. It's tempting to use Snowball Earth as a parable, but we should handle it with care. The Cryogenian was a world of slow levers, continents arranged to favor cooling, a dimmer sun, a carbon cycle operating over millions of years. Today's climate change is driven by a rapid injection of CO2 on human timescales, centuries, not geologic ages, and the feedbacks and risks are different. Still, there are echoes worth hearing. First, thresholds are real. Albedo, circulation, and greenhouse gases can lock a system into states that resist small nudges and then yield suddenly to big ones. Hysteresis, the different road in and out, means caution about pushing Earth toward edges we don't fully map. Second, feedbacks cut both ways. Dust that darkened ancient ice sped thaw. Water vapor amplified warming once melt began. Circulation changes reshaped oxygen and nutrients. Modern analogs exist. Ice albedo feedback at polar caps. Water vapor responses. Circulation shifts that alter oxygen in today's oceans, playing out faster and with living stakes we can measure. Third, recovery has terms. After Snowball, weathering drew CO2 down, but only because volcanoes had first raised it enormously, and because raw, unvegetated continents presented huge reactive surfaces to warm, acidic rain. Our landscapes are different. Our timescales are shorter. Our responsibilities are immediate. The lesson isn't Earth will fix it. It's Earth has gears, and we are currently leaning hard on some very fast ones. What Snowball can give us is perspective. Planets can wear very different stable faces and still host life. Life can be tough and small and persistent, then exuberant when constraints loosen. It also gives language, threshold, feedback, state that helps us think clearly about risk. Hold the humility of that for a moment. We are clever, but the system is older and has played longer games. Clarity, not comfort, is the gift here. Once you've met a snowball, you start seeing cousins. Mars bears scars of ancient water, but today is a desert deep freeze. Its thin air too weak to hold much warmth. More a fossil winter than a true snowball, but instructive. Icy moons like Europa and Enceladus wear hard shells over dark oceans warmed from below, with hydrothermal vents that may echo the lifeboats of our own deep freeze. Exoplanet models suggest that worlds at the cold edge of their stars' habitable zones can toggle into global ice, then thaw if volcanic CO2 accumulates. Climate states with memory, just like ours. These comparisons aren't about certainty, they're about possibility. A planet with a bright surface and thin air might need just a nudge, dust, a geyser of greenhouse gas, to tip between blue and white. A world locked in ice might still harbor metabolism in vent-lit rooms, awaiting a change in sky. Even here, in our solar system, Cassini saw jets at Enceladus rich in organics. Europa glows with hints of a salty ocean below. Snowball teaches us to look beneath bright silence for moving water and chemistry. For exoplanets, light curves and spectra whisper bulk truths. How reflective a world is. Whether its air carries CO2, methane, or oxygen. Whether oceans wink in glints. A very bright planet at a favorable distance could be in a snowball state. A very variable one might be dancing around thresholds. Someday we may read cap carbonate analogues from orbit. Unlikely. But the thought pleases the imagination. Bright mineral blankets as planetary signatures of sudden warmth after long cold. Hold the larger lesson close. Habitability is not a single number, but a landscape of states. Life's maps may include long winters with small hearths, then dawns with wide fields. Snowball Earth makes our own chapter feel both rarer and less alone. We've walked from a planet turned to glass to a sea that remembers how to breathe. From lifeboats in brine channels to soft bodies testing shape. From tubes as thin as paper to trilobites with polished eyes. Along the way, rock kept the minutes. Dropstones in calm mud, striations on bedrock, pale cap carbonates draped like frost after rain. Chemistry hummed the changes, carbon lightening at the cap, strontium rising with rivers, oxygen learning a steadier pulse. The moral is not that catastrophe makes beauty, but that release makes room. Snowball Earth tightened constraints until the only way out was a broad, patient reversal. Volcanoes thickening the sky, dust and ponds prying open the mirror, water vapor joining, rain returning, rivers rinsing continents into the sea. When the lid lifted, the ocean did what it has always done best. It circulated light, nutrients, and breath. Life, small and stubborn, stepped into the space that created, and complexity found a scaffold. If you listen now, you can still hear it. The hiss of wind on ice far away in time, the first warm rain on naked rock, the hush of a burrow roof giving way, the faint clink of a mineral plate forming along an organic mold. You can feel the patience in thresholds and the swiftness once they yield. and you can fall asleep to the knowledge that our world has worn many faces and kept time through them all.
When you wake, the sea outside your window will not be the cryogenians, but some rhythms remain. The pull of tides, the season's breath, the way light on water turns thought quiet. That's enough for tonight.